0 or N equal to mg. So you can see that the weight and the reaction forces are equal and opposite. Let's now look at some more reaction forces. Reaction forces come in many forms. We just looked at a couple of those. This is one form of a reaction force. When the object is sitting on a surface, the reaction force supports it. In other words, it balances the weight. Now, if my hand is not able to apply that reaction force, what will happen? The mass will keep falling. Now, why am I able to stand on the floor of the classroom? My weight is acting vertically down. If that is the only force on me, I will go straight to hell. Is that right? Yes, I would. Well, the floor will not allow me to do that. It supports me. So my weight is balanced by the normal force there. Now look at the traffic light. Now here is a traffic light there. I think some of it is blocked. You can see the traffic light is supported by two cables. Now the weight of the traffic light, now what are the forces acting on that traffic light, keeping it in position? Can you talk about some of the forces that are acting on this traffic light, keeping it in position? It is in equilibrium. What is the meaning that it is in equilibrium? Equilibrium is the state where the forces are balanced. That means no net force. When there is no net force, the object is either at rest or moving uniformly. The traffic light has to be at rest. That means the net force acting on it must be 0. The first and the important force there that you can identify is the weight of the light. That will be acting vertically down. Weight is mg, where m is the mass and of course g is the acceleration due to gravity. That acts vertically down. To prevent the light from falling freely, the cables apply forces upward. So there is a force on this cable on the left and this cable on the right. Now, these forces on the cable are called tension forces. If you stretch a spring, the spring applies a force backward. If you hang on a string, the string will support you as long as the tension on the string will hold up your weight. So the force on the cable is called the tension forces. That means there is a tension force on the left cable and I'm going to call that tension force T1. And there is a tension force on the cable on the right and I'm going to call that T2. Therefore, there are 3 forces acting on that light, keeping that in its position, keeping it in a state of equilibrium, in a state of balance. The vector sum of these 3 forces is 0. In other words, if you add the weight vector to the T1 vector to the T2 vector, the sum of those 3 force vectors will be 0. You can see here, we will be using the rules for vector addition to do these kind of things in problem solving. Now here, the action and reaction forces add to give you 0 because forces are acting on the same object, keeping at rest. So, the force pairs that we were talking about can be labeled as action forces and reaction forces. Now, if action forces and reaction forces are balanced, then we can actually make a statement of the third law. What is the statement of the third law? Action forces are balanced by the reaction forces. In other words, action is equal and opposite to reaction. That is actually the statement of the third law. Now tell me, what are the forces involved when a horse pulls a cart? Well, what we said is that action forces are equal and opposite to reaction forces. Well, take the case a horse is pulling a cart. Now, what is the action? The horse is pulling on the cart, is that right? Then shouldn't the cart pull the horse back? And if the action and reaction forces are balanced, that means that horse can never make the cart move. Now, do you understand what I'm saying? If action and reaction forces are equal and opposite, they cancel each other, then the force with which the horse is pulling the cart forward will be equal to the force with which the cart is pulling the horse back. That means the horse and the cart should be at perpetual rest. So why did we create the cart in the first place if the horse cannot move it? Can you explain the paradox here? What is the problem here? Well, do you see that the cart is tied to the horse? That means the horse and the cart forms a single system. So the action here is not the horse pulling the cart. The action here is the horse kicking the ground. See that? The horse is kicking the ground. That is the action. The horse kicks the ground backward with a force F sub K, the force of the kick. Now what is the reaction force here? The ground applies a force F sub R forward. In fact, in the absence of this reaction force, the horse and the cart will never be able to move. It is this reaction force that make the horse and the cart move forward. But then didn't we say that action and reaction forces always cancel each other? Well, yes, we did say that. But that is true only if the action and reaction forces act on the same object. In this case, the action, which is the weight, the reaction force, which is the normal force, are both on this mass. They cancel each other. But in the case of the horse and the cart, the action is by the horse on the earth. The horse doesn't like the earth. It keeps kicking the earth. You see that? That is the action. The action is the horse kicking the earth. What is the reaction? The reaction is the earth pushing the horse. It is a fight between the horse and the earth. Now tell me, how is it possible for you to walk? It's the same situation. When you want to walk, you kick the earth backward. The earth will push you forward. So it is a perpetual fight between people and the earth all the time. Thousands and thousands of people are kicking the earth. Now, shouldn't that kick move the earth? Well, we assume that because all these kicks are so random, the total effect of all that kicks will average out to be zero. So you kick the earth backward, the earth pushes you forward. If the earth doesn't push you forward, you will never be able to walk. Now try walking on a muddy place where it is full of mud. You put your foot down and your foot gets stuck. You see that? You cannot get the upward, the forward push from there. You can only walk on firm ground where the ground is able to push you forward. Now look at how a high jumper is able to jump. When the high jumper wants to jump, he pushes the earth down with a tremendous force downward and enabling the earth to lift him up. The merit doesn't go to the jumper, the merit goes to the earth actually. It is the earth that lifts up the high jumper. Well, of course, the merit goes to the jumper. You need to know how best to kick the earth. Alright, so action and reaction forces will cancel only if they are acting on the same object. In this case, they are not acting on the same object. When we walk, they are not acting on the same object. You see, force pairs are all over. They don't cancel very often because they are on two different objects. These two forces are on two different objects and they don't cancel. It is the reaction force of the ground that propels the horse and the cart forward. And it is the reaction force applied by the ground that makes it possible for us to walk on the ground. You see, look at the blessings of nature. If the earth one day refuses to push you forward, you will not be able to walk. So you must be thankful for all such blessings. Okay, when a rocket is fired, it is the reaction force of the exhausting gases that propels it forward. Now, the firing of the rocket will burn fuel and the exhaust will be pushed down, and the exhaust that is moving down will apply the reaction force upward, making the rocket to go. Now try blowing a balloon and leave it. You can see the air will come out of the balloon fast, the balloon will go back. It's the same principle as the rocket. Have you ever tried firing a gun? If you fire a .303, that's one of the old rifles. I have used one of those. Now, if you keep it on your shoulder and fire, the bullet goes very fast forward, that is the action. And in jumping out, the bullet will apply a reaction force backward. And you can actually feel it. If you don't keep the rifle properly, it can break your collarbone. So you must actually have training to use such rifles. Now, if you are in a boat, inside water, if you jump out of the boat, what happens to the boat? It'll go back. Action and reaction. When you jump forward, the reaction force takes the boat backward. Well, so all these illustrate that forces always come in pairs. But what I have done here is to lay the foundation for discussing the laws of motion. The three laws of motion. The first law, the law of inertia, helps us to define force. The second law enables us to measure force. And of course, the third law says all forces come in pairs. Well, what we're going to do in the next part of this lesson is to use these concepts to solve problems.